Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am very happy to have Shuyu Tan and Quentin Parker with us today. Hello, Shuyu. Hello, Quentin.
G'day. How you going?
I'm doing great. How you doing, Shuyu?
I'm good.
Okay. And Shuyu, where are you located at?
I'm currently working as a research assistant in the Laboratory for Space Research at the University of Hong Kong.
Very cool.
And yeah, I've been there for 3 years, and our office is in Cyberport. It has pretty nice sea view.
Okay. If you can adjust your mic a little bit, it would be good. You're a little far away, but we're okay. And Quentin, where are you located at?
I'm about 20 meters from Shuyu's desk. I'm actually also in the LSR. I'm the director of the LSR here at Cyberport in the wonderful city of Hong Kong.
Wonderful.
Looking out at the window at the islands out on from my window. Very wonderful.
And we are in Northern Hemisphere. So how's the summer going there? Is it wet? Is it sunny? What's the weather like in Hong Kong in the summer?
It was pretty hot last month because it was like a typical summer days, but it's getting some feeling of autumn from this week.
Well, it is August 17th, 2023 as we record this, and I'm in Phoenix, and it's definitely hot. And in fact, there's a hurricane off the coast of Mexico, and we're supposed to get a little bit of deluge of rain here over the next couple of days. So it'll be interesting. Hot and moist. Very cool. And Shuyu, what do you like to do for research?
Currently, working on Planetary Nebulae in the galactic bulge. That's the subcivics I'm currently studying.
I think you need to move your mic closer.
Hey, you can't hear you, Shuyu. You got to speak up and get closer to the mic, girl.
Yeah, get a little closer or bring it closer. But your sound is a little weak.
Try again. Did you want her to come into my office? Would that be easier?
Am I getting better?
Oh, there we go. That sounds good.
Yeah.
Okay.
Okay.
So now let's go back. So Shuyu, what do you like to research?
Yeah. I'm currently studying a sample of Planetary Nebulae in the galactic bulge, and so one aspect is to study those objects themselves to understand their morphologies, their chemical abundances. Another major job is to use them to trace the chemical evolution in the galaxy. And this is the major topic I'm interested in, the evolution of galaxies.
Very cool. Very cool. And Quentin, what do you like to do for research?
Oh, I like to live off my students. No, seriously, I mean, Shuyu is one of the best students I've ever had. And she's an MPhil. And at the end of it, I said, well, you've got like 5 papers here. There are 5 papers.
That's good. That's very good.
So we've got 2 published, and this is the 3rd. But I lead quite an important group in late stage stellar evolution at the University of Hong Kong. We're quite well known globally. We also have something called the HASH database. It's a world-class repository for all galactic planetary nebulae. It's called HASH. That's an acronym. I used to be at Macquarie University in Sydney, and it was called MASH, where M is Macquarie, but here H is Hong Kong. A is AAO, S is Strasbourg, and H is the H alpha Planetary Nebulae. And we have like over 1,000 registered users in about 101 countries, I think, at last.
Cool. Very nice.
So we're quite a strong group in late stage stellar evolution, Planetary Nebulae in particular.
Very cool. Very nice. And that is going to bring us to this very awesome APJ letter. It is open access. It's the open access era, people. You can go get a copy for free. Go grab one. When the stars align, a 5 sigma concordance of planetary nebulae major axes in the center of our galaxy. And Shuyu, Quentin, take us away. Shuyu, why don't you start off?
Yes, you start, Shuyu.
Oh, okay. And so like this paper is talking about funding from our research, and we found there are 16 planetary nebulae in the galactic bulge. They're aligned and they're almost go parallel to the galactic plane, and the statistical significance is quite significant. It achieved 5 sigma.
Mm-hmm.
Yeah, and so that might have some implication for the future study on galactic evolution.
Okay.
And 5 sigma is like 1 in 3 and a bit million counts. So it's counted as a discovery in science. You know, but the samples she mentioned of 16, I mean, these are all PN that either host or have inferred to host close binary central stars. No other PN in the entire sample show any alignment. They're completely random. This is we discovered where this alignment comes from. That's the kick.
Right. It's very specific type.
Hmm.
Very cool. Very cool. How about give me a little history? Seems like it was 1968.
Yeah. So like this work is actually motivated by a few previous studies and some researches previously on galactic PN has found an alignment where concentration on the position angle distribution of planetary nebulae, and it's around 90 to 100 degree.
Okay.
And I think back to 2013, a previous work by Dr. Rees, he found a specific sample of planetary nebulae. Those who have bipolar morphologies are aligned, and the signal is around 3 sigma, and it applies to bipolar planetary nebulae only. So I was trying to do is to remeasure the position angles for all the objects from our excellent VLT imaging observations in combination with 40 images, PA images from HST.
Cool.
And with the updated measurements, and I reanalyzed the position angles, and I actually found that according to our better the definition of bipolar PN, this alignment found previously on bipolar PN is not seem to be very strong as previously reported.
Okay.
But I was thinking, no, it was actually briefly mentioned in the previous paper that it might be due to some wild binary orbits.
Okay.
That's the reason to make those objects aligned. So I selected those samples with observed, observationally confirmed short period binaries. So it's different from what they mentioned before. There are short period binaries. Okay. And originally there were 5 objects, and I found that their position angles are like highly concentrated at around 9 to 100 degrees, and the spread was quite low. It's around 5 sigma, or sorry, it was around 5 degrees. So it's a pretty strong signal. And then I showed the result to my supervisor, Professor Parker, and we just ate those that are highly likely to host short period binaries. So that gives the final sample used in this paper. Very cool.
Yeah, that was my brainwave, that the small sample that Shuyu had, we could double it in size by saying, hang on a minute, this is result from Roger Wesson, who showed that PN that have high abundance discrepancy factors, if you look at those, they're all in short period binaries. Now, the previous work from Rees and Zylstra was a different sample of data to ours, and they actually classified PN in a different way to what we did, because we classify our objects as PN as bipolars based on the hash formula that we, that's now, used by everybody. So we're consistent with what's out there and what we've led. And now we added this extra sample, and then lo and behold, they actually doubled the sample and the signal's still exactly the same. So now we really have something to play with. We're not, it's only half a dozen objects. Who's going to believe that? So suddenly we got, 14 objects or so, and now it's a significant. The fact that they're all bipolars is something about the way that bipolars form in binary systems, the way that they constrain the ejector in certain directions when you're in a tight binary orbit. But then so that's why they're bipolars. But it's related to. But all bipolars don't show this. If you take out the sample that we found that are in short period binaries or inferred to be in short period binaries, and look at the rest of the bipolars on their own and look at their alignments, there aren't any. They're random.
Yeah.
So this is the key. It's just this, and that's what nobody else had. And that's why we've gone from 3 sigma to 5 sigma significance and gone from, oh, it's bipolars to no, it's PN in short period binaries, which are bipolars.
Cool. Very good. And I think we have an example here in figure 1.
Yeah, like the example is showing our practice for the measurement of position angles of planetary nebulae. So a position angle is basically defined for every either elliptical or bipolar PN. So the right and the left and the right are showing a typical example of elliptical and bipolar PN. We actually have a detailed description for the morphology of PN and presented in our paper 1. And for the we basically measure the angle, like from the galactic north to the galactic east, and of the axis is defined as the major axis of the elliptical PN, or the like a long symmetric axis of a bipolar PN.
Very good. Okay, that's the geometry, and we talked a little bit about the selection of those objects, the observations that were done. I think we got here's hash. If people want to go to hash, if you don't know what that is, go check it out. And here's a couple of the PNN. Okay.
Yes, like this table is presents our sample using the study, and the part A is showing those with observationally confirmed short period binaries, either from TESS or Kepler or some ground-based observations. There is a pretty nice catalog organized by Dr. David Jones. Yeah, and it's actually mentioned in this paper, so I just accessed the data from the web page, and I found that those like 7 objects have observationally confirmed PN. Also, this for the last objects is not very certain, so we excluded from our analysis. And the part B table is showing the objects with high abundance discrepancy factor, which was measured, which was measured by their spectroscopic observations from BLT, as well as also will be presented in our future paper.
Cool.
And there is a clear cutoff, like if a PN has an ADF over 18, yeah, it's highly likely to have a bipolar central star, based on previously statistical studies.
So we select central star for you. So not bipolar.
Sorry, have short period binary central stars. So we selected those objects with an ADF over 18, and so that gives another part of our sample. There are actually 9 objects, but the 4th one, it's actually a round object, so we can't measure its position angle. We also excluded it from our analysis.
Okay. All right. Cool. So there we have, there's our samples. And
you notice that in that table, they're not all bipolars. There's one round that could possibly be a bipolar seen face on, looking down the pipe. That's a possibility. There are a couple of objects known like that. And it's also, as you see there, that in our classification, there's an EMRS, which means it's an elliptical. But again, you know, if you don't have the high quality imagery, or it's not quite as deep, sometimes ellipticals turn out to be bipolars when you get better imagery. Right. So, you know, we're just being honest to the data we have, and we just classify them as best we can. It is somewhat subjective morphological classification.
Sure, sure. Zooniverse, here we come. And then we sort of get in the meat of it is, how do we measure those position angles?
Well, I think Shuyu can explain here that, you know, the EPAs, which you saw in the previous plot, have to be converted to a GPA so you can compare everything in the same way. So would you like to say something about that, Shuyu?
Oh yeah. So I've introduced how we did the measurement of APAs as like the angle made between the galactic north and with their major axis, and so with the APA and their galactic location, we can use these two formulas here to convert it into galactic position angle.
Mm-hmm.
So that gives their position angle relative to the galaxy.
Cool.
Or in the galaxy.
And then we start our statistical analysis. So we have frequentists and Bayesians, Monte Carlos.
I mean, Shuyu really went to town here. She has a great and deep interest in statistics. And I used to when I was her age, but I'm slightly older now. But she did an absolutely brilliant job of absolutely nailing the statistical significance of this result. So if you didn't like this test, well, here's another one, and another one, and another one, and Bayesian. There you go. So she absolutely nailed it. I know the AppJ letter got a specific statistical editor to check everything out, which one we passed with flying colors. So we're extremely confident in our results. So I'll let Shuyu explain all this fantastic work.
Yes. So in order to test the statistical significance of our results, the first thing we have to notice is that those position angles are circular data. They have some periodic features, so we can't use those other tests or method used for the ordinary data.
Okay.
So there are a few frequentist statistical tests we can use to test whether their distributions are random. And it was actually used in previous studies as well. And I used some of the tests from the NICE-R packages. And that gives part of the results in the table below.
Table below. Let's go to that table below and take a peek.
Like this table.
Oh, very good.
For the for the like the 2 to 5 columns, they start showing the results from frequentist statistical tests.
Mm-hmm.
And another thing we can do is we randomly picking angles from a uniform distribution to see the likelihood that it could give the observed sigma sigma of the it's like a standard deviation of the position angles we observed for each sample. So that gives the 6 column. So that's the likelihood estimated from Monte Carlo methods.
Cool. Good. Okay.
Just by randomly picking angles. And the lesser column is based on the fact that we already found our result is likely to be highly non-random. And I use Bayes factor to compare to test whether our data face a uniform distribution, where it face some unimodule distribution with certain concentrations in the last column.
Okay. Yep. Log B. That's our Bayes factor. Mm-hmm. Very good.
And
so as you can see from the table, you've got like the entire sample, its statistical significance for any alignment. The non-short period binary sample is 112. The bipolars 93. The bipolars, but which are not in short period binaries, 81. And you can see all of those values are very low significance. Only the last row there stands out so clearly, because that's where all the signal comes from. In the other results and the other work that's been done in the past, where they found various levels of statistical significance which nobody really believed, is because the signal's diluted. The real signal was there, but it was diluted amongst everything else. We've now isolated where that signal is coming from, and that's the key discovery.
Nice. Very nice. Beautiful. Very beautiful. Very good. And we have a distribution here on the sky.
Wow. Great plot.
Yeah, very nice. Okay.
Go on, Shuyu. You can talk about this.
Yeah, so this is actually the major result of this paper. We're showing the distribution of galactic position angles of each object, and those in blue are the observationally confirmed short period binary objects, and those vectors in pink are showing those objects with high abundance discrepancy factors, and the blue one actually have an uncertain observations of its central stars, so it's likely to host a short period binary from the observations.
Okay, so how about the green one here?
Yeah, so we like added it into the plot, but didn't count it into the analysis.
Okay.
Suspected of hosting a short period binary, but not yet proven. So, which is a pity because it actually perfectly agrees with our thesis of what it is. So we suspect it really is a short period binary. And once we get that data, we'll add it into the mix and it will make the statistical significance even greater. Notice there's M2-19, which is not aligned like the others, but it's almost 90 degrees. So it's possible to look at some binaries, bipolars, is that sometimes when major axis, it could be one or the other. And so that's a possibility here. But nevertheless, I think it's clear when you look at the rest of the sample, which are in the gray vectors, that things are pretty much random, as proved by the statistics in the table.
Right. Yeah. Okay. Very nice. Very nice. I love that shot. Very cool. Very cool. Okay. Figure 2. We have some summaries, and I think we got one more plot. Finger plots. What are finger plots?
These are the key results here that you can see. Shuyu, again, go on, explain this to the listeners.
What is a finger plot?
Yeah, these are some statistical plots we made to show the distribution of circular data. So the first one is a finger plot. It's like basically just showing all the data points on a circle.
Okay.
Yes. The line here is showing the
same color coding as in figure.
Yes.
Okay.
Exactly.
I'm with you. I'm with you. Okay.
Yeah. So the top row is showing the result for the whole sample. So all the PN in the galactic bulge we observed, and the second row is showing the plots for our short period binary sample only. Okay.
Yeah. What is C and G showing? What are these colors?
These are called vector plots, and like each short segment is showing the position angle of a single object. Of a single object. We're just adding them up, like connecting the measurements of different objects.
Got it.
And those one in colors are ordered by their galactic coordinates, and the outer right curve is showing the plots ordered by their position angles.
Okay.
So so for the right curve, the more it's close to a circle, the more random it is.
Okay, I'm with you. Gotcha.
Yeah.
Okay, very nice. Finger plots. I learned something.
Well, it's circular statistics, so we have to use these kind of presentations.
Speaking of, and there's 2 very nice appendices with more of it, so people should check that out. Very good. Excellent work. And of course, this really begs the question, kind of, why?
Exactly.
Why would be a nebula be aligned?
Spooky, bizarre, mysterious. People are going to have to try to explain this, and I think that's the hard. Magnetic fields spring to mind. That's the obvious idea that But the point is that the PN in this sample aren't all of the same age. When you look at the ways that we can work out the ages of some of these PN, it's true that bipolars generally come from higher mass progenitors and are therefore thought to be younger. But there's at least a giga year or two difference between some of these PN. in terms of when they were born. You know, they're all going through the PN phase now. So this is like a snapshot of stellar death instantaneously, because PN only lasts for a few tens of thousands of years, and their progenitors last for hundreds of millions to billions of years. And so they're all happening now. So this alignment we're seeing is right now. 10,000 years, it'll be a different sample that may not be aligned. But this is what's aligned now. And when you look at that, are you saying, well, how on earth could this be? Is the orbits frozen in at birth when the binary stars are formed in maybe closer binaries than others, that orbital inclination is frozen in, because the orbital inclination is at 90 degrees to the bipolar ejector. Right. You know, you have the plane of the orbit of the binary, and then you have the ejector coming out 90 degrees to that. Yep. You know, in the way that these things work. When one of the stars in the binary system is going through the PN phase, only one of them, because they don't have exactly the same mass, and therefore they don't go through a PN phase at the same time. Sure. And so you've got to explain this. So, okay, these binary orbits are frozen in at birth. They're difference in ages of billions of years potentially, and across vast volumes of the galaxy. Right. How is this alignment happening? And there's a galactic magnetic field extant over billions of years that's sufficiently robust, sufficiently ordered, yes, to actually create this. If yes, not, the only alternative is that alignment has been happening now. But how? What is the force that can do that? Magnetic fields in the galaxy at the moment don't have the strength, theoretically, to do according to the work. So, you know, theorists need to, you know, figure out what the hell's going on. Observationalists here, we're just presenting this wonderful discovery, an amazing result, bizarre and ghostly, you know, and now, you know, cleverer people than myself will have to figure it out. Very cool. I think you can, because you're cleverer than me, I think. Very cool.
No, I'm not.
I hate to differ there. Okay, very cool. Very cool. And like I mentioned, there's 2 appendices that have additional plots of the images and the angles. So do check that out. And then the last one is some corner plots from the Bayesian. So very nice. Very cool. Yeah.
We're very excited because a guy, an influencer who's got like 1.2 million subscribers, picked up our paper as well and did a 10-minute YouTube video on it. So it's slightly different. It's crazy. So there's a nice article coming out in the Ether magazine on this story too, and it got quite a good press around the world. So hats off to my wonderful students, and she was so good I had to keep her on as an RA for a year to get all these papers out. Absolutely. So that's what we're doing right now, and we may have another App J letters paper from all this work on something called the sulfur anomaly.
Okay, I like sulfur. I like sulfur. Very cool. Very cool. Well, clearly there's a lot of work to do on this topic, both, you know, increasing sample size. So let me just ask, you know, where do you think we go besides your next immediate APJ letter paper? Where do we sort of go with this over the next 2 to 5 years? Is there observational campaigns? Maybe we do them at different wavelengths, different instruments? Is there theoretical work to be done? Just where do you think we go over the next couple of years? Shuyu?
2 to 5 couple of years, and maybe
we find more examples. We need to actually
yeah, that's the first thing.
Short period binaries if we can. That's going to need a lot of effort. We won't do all of that. Other groups, I'm sure, will come in and help, but that's clearly needed to you know, look, it's 5 sigma, so the discovery is there. It's just no adding to it. You know, and maybe looking for subtleties. You know, you may have noticed that maybe the short period binary sample don't exactly have the same average orientation as those that are high ADFs, although they are very closely aligned. Maybe there's a slight difference. Is that some subtle clue there as to what's going on? You know, so those things can be investigated.
And also the theoretical investigations of the formation of stars at the very beginning of the star formation in the galaxy, and how does magnetic field affect those processes.
Right. Very cool. Very cool.
That's a mystery. You know, there's recent stuff has come out about MOND. It's all, you know, you must have heard about that. The proof, again, high statistical significance about, you know, about the non-Newtonian gravity. And you know, is that somehow also at play here? I was thinking, just So I don't know. Is it just magnetic fields, or is it magnetic fields with something else? Because it doesn't look like the magnetic fields are currently strong enough to align the bipolar lobes. And well, it's the orbit of the binary system that's the key here.
Very cool. Very good.
Yeah.
Well, I really look forward to seeing this one evolve over the next couple of years. This will be very interesting, one way or the other.
We're really happy. You know, it's funny, you know, the way that science works sometimes. You're doing a work, you're working on abundances principally, and then, you know, we said, well, we might as well do the GPAs because we can. We got good quality data from the VLT. Some of the best imaging of these PN that exists has enabled us to measure high quality angles for the first time for many of these PN, and that has enabled us to do this side thing. And then when Shuyu came to me with a small sample, and I said, well, we could double that sample because we can use the ADFs as a proxy, suddenly we think, oh my God, drop everything. We're writing up this straight away. So we did. And this is the result. But we, you know, it's science works like that way sometimes. But it's like realizing that and thinking, aha, you know, and then grabbing that opportunity and running with it and creating this paper. It's been a huge pleasure to work with Shuyu on this paper. You know, it's just a wonderful result.
Dr. Shuyu.
No, it's MPhil. You know, I mean, to be honest with you, she's got more out of an MPhil than most people get out of a PhD. Okay. Seriously, in 5 papers. Come on,
yeah, that's crazy.
A PhD now. You know,
well, I'll give you one. Okay, so I'm calling it Dr. Shuyu.
No,
very cool. Shuyu,
she's after a PhD place. If anybody has one that wants somebody of her quality,
yeah, please.
There's an ad, people. Grab her.
She's an ad. She deserves one. She's brilliant.
Grab her. Very good. Shuyu, Quentin, I want to thank you so much for spending some time and walking us through your very lovely APJ letter. Thank you.
Thank you so much.
Thank you so much. Thank you for the invitation.
Bye-bye, Francis. Thank you.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.